Hello everyone. In this video we're going to go over section 10.2 part 2 of the examples. So now we're in question number 8 and we have an adjacency matrix here with 6 nodes. We want to know how many connected components this graph has and identify the vertex x. So this is something that can be done in any order. For example, the questions are how many connected components do we have, identify vertex x, draw the graph, draw the components separately, what features of the matrix tell you immediately that the graph is disconnected. Well, one of the things like you see the matrix, you see a connection between the nodes 1, 2, and 3. And then you see another connection between the nodes 4, 5, and 6. And it's like in 2 blocks. You see that you have a block here, you have a block here, you have zeros here. So it means that node 1, 2, 3 are connected, node 4, 5, 6 are connected, but they don't have any connection between them. So that's how you know that you have 2 connected components. And it's going to be 1 connected components by the node B1, B2, B3. And it's going to be 1 connected component by the nodes B4, B5, B6. We can actually draw those connections. Let's see, we can write B1, B2, B3, and let's write B4, B5, and B6. And now notice MB1 1 is connected to 2 and 3. So we have connections like this and like this. 2 is connected to 1 and to 3. So we have this connection already. We have this. 3 is connected to 2 and to 1. So this is the connection that we have. Now notice that we have exactly the same connections for B4, B5, and B6. So they're exactly connected in the same way. And these are the 2 connected components. This is the graph. They're disconnected. Immediately you can notice that they're disconnected, so the graph is disconnected. And the fact that this is in blocks, we have 2 separated blocks. 2 separated blocks. And that's going to mean that this is a disconnected matrix. We have the block diagonal structure here. Okay, so that pretty much matches our theorem for connected components and for block connections in a matrix. All right, so for question number 9, we want to determine whether 2 graph velocities are isomorphic, and if not, let's identify the invariants that differ. If yes, then we want to explicitly show the bijection. So first we go for the sequence of degrees of the nodes. So we're gonna go with the nodes for the degrees for A, B, C, and D, and we're gonna put it in that order. Notice that the number of edges going out of A are 3, so we have 3. The number of edges out of 2 is 2. Out of C is 3, and out of D is 2. So we do have that sequence. And notice the order that I'm following. I went A, B, C, and D. Now if I go to G prime, I'm following X, Y, C, W as my sequence of nodes to check the degrees. And you can see that they have the same matching sequence of degrees. You have 3, 2, 3, 2. So in conclusion, they are going to be isomorphic. Notice that they're both of them, they have 4 vertex, and they also have 1, 2, 3, 5 edges. They have the same sequence of degrees. So in conclusion, they're isomorphic. Now, the mapping is kind of obvious. We can kind of map A to X in here. We can map B to Y. We can map C to C and D to W. So we should be doing mappings that go between nodes of the same degree, and also that they're connecting in a similar way on the other side of the graph. In this case, it's kind of simple to know that that's going to be the case, but later we're going to verify in question 11 a case where it's not that obvious. Okay, but first let's go for question number 10. In question number 10, we want to find two different spanning trees for the graph below and state what edges you remove. So first and anything, notice that a spanning tree is of course going to be a tree that that joins all the or that has all the nodes included. We cannot leave nodes out because we have 6 nodes. The spanning tree should have 6 nodes minus 1. It's always n minus 1, right? So we should have 5 edges, right? So the spanning tree is going to have 5 edges. So I can make a spanning tree with 5 edges. So I gotta go and write A, B, C, D, E, and F, and make use of 5 edges to get that spanning tree. So for example, one of them can be, I'm gonna start here at F, I go here, then here, then here, then here. I got 1, 2, 3, 4. I got one more, 5. And this is an spanning tree of this. I just cut 1, 2, and 3 edges. I remove AE. I remove BF. And I also remove EF. Okay. Now let's do another example because you can have multiple spanning trees. Of course, there are plenty of connected spanning trees that you can have here. But that's not only the case. You can also have disconnected spanning trees. As long as it has a tree shape, then it's going to be fine. So for example, we can go with, let's join B and C. Let's join A and D, E, and also F. Now we have 4. We can do one more. We can do this one. Okay. And here we're removing AB. We'll also removing CF, and we're also removing BF. Can I get more spanning trees? Sure. You can get a bunch of different spanning trees depending on where you're going and what you're removing. You can do a bunch of different of those. But the condition is that you need to have, for the spanning tree, you need to have 5 edges because you have 6 nodes. There's always going to be 5 minus 1. And of course, you're looking to build trees that are advantageous to you and whatever you're going to do, especially if this is going to represent in some sort of algorithm. You often want to do something that is going to be easy to navigate so you can cover multiple options. All right, now let's move to question 11. All right, so now for question 11, consider the following 2 graphs. We have the graph H and the H prime. H has the nodes 1, 2, 3, 4, and H prime has the nodes P, Q, R, S. So we want to verify that the invariants match. Essentially, we can write an isomorphism from H to H prime. The invariants are scores. The first one is the same number of edges and the same number of nodes, and we have 4 nodes for both, right? And we also have 4 edges. So that is the first invariant. The second invariant is going to be the degrees. So we can verify that the degrees of H, the sequence for degrees of H, is going to be 2, 2, 2, 2. So all the nodes have degree 2. Just remove the comma from here. For H prime, they also all have degree 2. Notice P has 2 edges going out, S has 2 edges going out, Q has 2 edges going out, and R has 2 edges going out. So it's only 2, 2, 2, and 2. So now both graphs are cycles with 4 nodes, and they're connected. So all the invariants are matching. So connected cycles. So now let's write a specific isomorphism from here. The way that we want to write this is in a way that would match how the node distribution are, and so we can match also how the edges are distributed. So we're gonna go with 1 is going to P, then 2 is going to R, then 3 is going to Q, and 4 is going to S. Now with that, we're sending the edge 1, 2. So this is nodes. And so now the edges, we're sending the node 1, 2 to the PR, right? So this 1, 2 goes to the PR, so this one. Now we're sending the 2, 3, the edge 2, 3 is going to be sent to the RQ. So notice that this one, 2, 3, goes to the RQ, so it goes to this one. Then the 3, 4 is going to go to QS. And the 4, 1 is going to go to the SP. Okay. So now if we check, one of the ways to verify that this is going to be a good isomorphism is verifying the adjacency matrix and verifying that the adjacency matrix is the same. So the adjacency matrix for H, we can see that 1 is connected to 2 and to 4. So 0, 1, 0, 1. Now 2 is connected to 1 and to 3. So 1, 0, 1, 0. 3 is connected to 2 and 4. So 0, 1, 0, 1. And 4 is connected to 1 and 3. So we have this matrix over here. So now the adjacency matrix for H prime is going to go with the ordering, of course, of the nodes. So we're verifying PRQS being sent to PRQS. And so P is sent to R and to S. So we have 0, 1, 0, 1. Now R is related with P and is related with Q. So we have over here. And then Q is related to R and related to S. So we have a 1 in here, 1 in here, 0 here, 0 here. And S is related to P and to Q. So we have 1 here, 1 here. And then you can see that we essentially have the same adjacency matrix. So they're going to be equivalent. And we can confirm that they're the same graph essentially under an isomorphism. All right, so now for question 12, we have a connected graph that has 8 vertices. So we want to know how many edges does a spanning tree for this graph has. Once again, we can use the n-1 edge theorem, and if we have 8 vertices, then we're going to have 8 minus 1 a minus 1 edges, right? So we can have a spanning tree with 7 edges. Now, if it says if the original graph has 14 edges, how many edges must be removed in order to obtain a spanning tree? Well, because we need to have 7 edges, then 14 minus whatever we're removing, it must be 7. So in this case, I just find out what R is, which is going to be 7 as well. And so removing 7 is going to give me a spanning tree. All right, so that was a conceptual question. Now let's go to question number 13, which is an application of this for network communications. So a communication networks links computers C1, C2, C3, C4, C5 with the following direct connections. We have C1's is joined to C2, C1 is joined to C3, C2 is joined to C3, C2 is joined to C4, C3 is joined to C5, and C4 is going to C5. So it says, let's write a adjacency matrix for this network. We can do that by just checking the connections between all of them. So we can just write C1, C2, C3, C4, and C5. And we can have the same structure on the top. So it's going to be C1, C2, C3, C4, C5. So C1 is joined by C2, so that means that we're going to have a 1 here. C1 is also joined by C3, and then we're going to have 0 otherwise because we don't have C1 joining with anything else. C2 joins with C3, and C2 joins with C4 also. And we have that C2 is joining with C1 from before. So that's something that we're going to have in there. Now, C3. We have information that C3 is joined with C5. So we're going to have this. And from before, we had information that C3 was joined with C1 and with C2 too. So we're going to have this and this being zeros. Now C4 is joining with C5. So we know we're going to have a 1 here. And we also have that C4 was joined with C2. We don't have anything else, so we have a bunch of zeros in here. Now C5 is joined with C4. So we have a 1 here. It's not joined with itself. And C5 is also joined with C3. You can see it here. So we can have this. Okay, and so that's our adjacency matrix. Now, we want to use A squared to determine is there any lane to communication path from C1 to C4, and how many are there? So that's a question for the matrix A squared, right? And because we're going from C1 to C4, we just need the component A14. Do we need to do the entire matrix multiplication? No. You know your linear algebra, then you can know that you can just simply go and set the sum of A1k times AK4. And k is gonna go k is gonna go here up to just the sum of all the possible members that we can have. So k will go from k equals 1 to 5 here. And then that's going to be the multiplication of the row by column of this. So we will have, if we multiply that row by column, we're going to get that this is 1 times 1 plus 1 times 0 plus 0 plus 0 plus 0. So we're essentially going to get 1. Okay? So there is going to be 1 length 2 path from C1 to C4. Now, this is something that, of course, you can navigate through the adjacency matrix. You can see how from C1 we can go to C4. And it's essentially going from C1, I go to C2. And then from C2, I go to C4. You can kind of see it from here too. From C1, I go to C2. From C2, I go to C4. That is something from length 2. So that's going to be my path in there. Now it says a power failure destroy connections C2, C3, and C2, C4. Does the remainder network has a spanning tree? Either find one or explain why it cannot exist. Notice that if I'm eliminating, so I'm eliminating C2, C3, C2, C4. So let me erase this here. So I'm eliminating C2, C3, and I'm eliminating C2, C4. So I just have this one, which is from C1. Or let me just make a picture, because why not? I'm just gonna do node 1. I'm just gonna do node 2, node 3, 4, and 5. And so 1 goes to 2, 1 goes to 3, we have 3 goes to 5. So let me just erase this one here. I'm going to put 4 here. So 3 goes to 5. And we have 4 goes to 5. So now how many edges we have? We have 4 edges with the connection. So if I eliminate this 2, I already have a spanning tree because it has 4 edges, which is enough to have a spanning tree. And this is clearly a tree, this connection, and I'm covering all the nodes, which is good. And I have 4 edges, so this is already a spanning tree. So the answer is yes. We have the spanning tree in there. Okay, question 14. All right, now in question 14, we have two graphs G and G prime have 5 vertices and 6 edges with degree sequence 2, 2, 2, 2, 4. We want to A, draw a two non-isomorphic graph satisfying this constraint is possible, or explain why all such graphs must be isomorphic. Well, the real thing here is that all these graphs are going to be isomorphic. There's not going to be an opportunity that they're not. And the reason why, notice that we have the degrees here at the vertex. We have 5 vertexes, and we have 1 that has degree 4. So that means that there's 1 vertex that is connected to all the other 4 vertex. So if we have, I don't know, the last one, this is vertex 5, and I have here 1, 2, 3, and 4, then there is no other option. This is going to be connected to all of them. And once that you have those connections, then for being degree 2, that means that it needs to be connected to another node, and that's it. So we're going to have, for example, 1 connected to 2, and 3 connected to 4, and that's it. There's not going to be any other option for graphs, since everything else has to be degree 2. So this is pretty much going to be the only graph that is possible that is going to have this degree sequence, and that is going to have 5 vertices and 6 edges. If you connect more, then it's not going to be any more following that sequence. So this is the only graph that can possibly do that. Now, if we compute the adjacency matrix for each of these graphs, so notice that this is going to be G and G prime as well. Then we can compute the adjacency matrix here. We can go 1, 2, 3, 4, 5, and of course it's going to be 1, 2, 3, 4, 5 as well. 1 is connected to 2 and is connected to 5. 2 is connected to 1 and is also connected to 5. 3 is connected to 4 and to 5. And 4 is connected to 3 and to 5. And last 5 is connected to everyone but itself. So this is going to be the adjacency matrix for this. Now, this is also asking to find the number of length 2 walks from a degree 4 vertex to itself. So pretty much this is talking about A squared. And if we're talking about the degree 4 vertex to itself, we're talking about going to 5. So in this case, it will be 5 to 5. And so that will be all the possible combinations that we can have in here that they give me the sum. So if you do the square and multiply this, then you're gonna have essentially that this row is multiplying with a column, and you're gonna have that this is 4. So you're gonna have 4 possible walks of length 2. Once again, if you want to take a look at this, just verify by multiplying the matrix by itself, and you're going to see that when you find a component A55, then you're going to have a number 4 on it. All right? Okay, so this is the end of the exercises for 10.2.